And I know you're looking forward to talking about matrices, and we will talk about matrices, but not yet. We're going to start somewhere else. So this is a problem that was sort of a continuation of the ideas of last time, and this is where we're starting. So find the general solution. We have two equations. X double prime plus y double prime minus 3x prime minus y prime minus 2x plus 2y equals 0. 2x double prime plus 3y double prime minus 9x prime minus 2y prime minus 4x plus 6y equals 0. Like, wow, what a problem. What a problem here. So, what do we do? Now, if we think back to what we did last time, most of the time we're like, oh, these aren't so bad. We just like solve for x or solve for y in one of the two equations and substitute into the other one. And life was good. Life was good. Can we do that here? Is it possible to get either x or y by itself in one of these two equations? No. And so our thought is, uh-oh. Does that mean we have to do that other thing we talked about? Yes. Now you might say, wait, there was something else we talked about? And so that was, we had sort of this sort of variation of Cramer's rule. And so how did that work? Well, first thing, let's just start by rewriting this. So this is the same as x double prime minus 3x prime minus 2x. And you'll notice what I'm doing is I'm putting the x's together. X double prime minus 3x prime minus 2x. And then plus y double prime minus y prime plus 2y equals 0. And the other would become 2x double prime minus 9x prime minus 4x. And then we're going to add 3y double prime minus 2y prime plus 6y equals 0. So in other words, we're grabbing all the x's together and all the y's together. This is not a bad idea. It really says, okay, can we see how they all fit together? And maybe we see, aha, there is something we can do. And no, substitution still is not going to work. But now the great, hey, we can think about these things in a slightly different way. So, where do we go from here? Do you remember what we did? Okay, someone said, don't we use the D? Yes, the D notation here. So, we call D equals take derivative. So this is just a callback. So when we talk about the D notation, that's what it means. So what would dx be? Derivative of x, also known as x prime. dy, y prime. How about dt squared? 2t. And I should say here in this problem, even though it's not said explicitly, we're not thinking of y as a function of x here. We're not thinking of x as a function of y. When we talk about systems of equations, we're really thinking of them as being functions of some other variable. So y is some function of t, x is some function of t. They might say, why t? And the answer is, well, it's just a symbol. We can use any symbol we want. The reason I'm choosing t is that it feels like a good variable name. And so oftentimes you'll see variables tend to be towards the end of the alphabet. T, X, Y, Z, U. And so that's just convention. But we could put anything we wanted here. We could put a little smiley face. It's just a little bit tiresome to write smiley faces. All right, so now we're going to use that notation and rewrite our relationship. So for example, x double prime minus 3x prime minus 2x. Using this symbol d, how does that become? Or what does it become? d squared minus 3d minus 2 times x. Okay, how about this y double prime minus y prime plus 2y? d squared minus d plus 2 and times y. 2 to go. 2x double prime minus 9x prime minus 4x. 2d squared minus 9d minus 4 times x. Last one, 3y double prime minus 2y prime plus 6y. 3d squared minus 2d plus 6 times y. And I should write down equals 0 equals 0. And now in this format, we say, ooh, this kind of feels like very matrixy. And you might say, well, what makes something feel very matrixy? Well, in that we have this nice linear combination. Something x, something y, something x, something y. That's a nice two equations involving x and y. And so we can write that in the following way. We have a 2 by 2 matrix, d squared minus 3d minus 2, d squared minus d plus 2, 2d squared minus 9d minus 4, 3d squared minus 2d plus 6, times xy equals 0, 0. All right. And once we got here, we said, you know, there's a way to get x and to get y from this. And this is where we had that variation of Cramer's rule coming into play. All right, so do you remember what to do? Let's say we want x. How do we get x? Okay, so determinant of what's on the left-hand side. So there are d squared minus 3d minus 2, d squared minus d plus 2, 2d squared minus 9d minus 4, 3d squared minus 2d plus 6, times x equals something. Okay, what goes over here? Yeah, so you should think of it when you have this matrix here. See how we have x, y? You should think of it as x is associated with the first column, y is associated with the second column. So when I'm solving for x, I come to the column associated with x and I replace it by what's over here, 0, 0. And then the other column, in this case there's just one. If there had been multiple columns, we leave those alone. All right, now one of these sides is really easy to do, and the other side it's going to be an onion problem. There are going to be layers involved, and maybe a couple tears shed along the way. Which side is the easy side? Yeah, it's good that you can spot that right away. What makes it easy? All those zeros. So it's 0. Okay, now the fun begins. You're probably thinking, it's been fun this whole time, Steve. What do you mean it begins? All right, you'll see. All right. So, here we go. Take the determinant, you do our diagonal. So that's d squared minus 3d minus 2 times 3d squared minus 2d plus 6. Subtract our other diagonal, 2d squared minus 9d minus 4, d squared minus d plus 2. All of that, x. All right. Good times. Good times. Now, what's next? Oh, I forgot. I ran out of space. What does all this equal? 0. Equals 0. Yes. All that equals 0. Okay, what's our next step? Okay, we're going to expand here. Good times. So, this is like foiling. But foiling, if you might remember, first, outer, inner, last. It's how you expand things. Well, here there's 3 pieces in each term. So it's not first, outer, inner, last, but you take the philosophy of foiling. The philosophy of foiling says you take one piece from the first and one piece from the second, and you do it in all possible ways. So let's start. D squared times 3d squared. 3d to the fourth. Good. D squared minus 2d. Minus 2d cubed. D squared times 6. 6d squared. Okay, so that's the first one with all possible. Go to the next one. Minus 3d times 3d squared. Minus 9d cubed. Minus 3d times minus 2d. Plus 6d squared. Minus 3d times 6. Minus 18d. Minus 2 times 3d squared. Minus 6d squared. Minus 2 times minus 2d. Plus 4d. Minus 2 times 6. Minus 12. Now that's the first one. Halfway. Now we're going to subtract the next pair. 2d squared times d squared. 2d to the fourth. And we subtract. So subtract 2d to the fourth. 2d squared times minus d. Minus 2d squared. Then we subtract that, so it becomes 2d cubed. I can do that. But we need to add it, because we're subtracting a negative. 2d squared times 2. 4d squared, and we subtract. All right, move to the next. Minus 9d times d squared. Minus 9d cubed, and subtract that becomes plus 9d cubed. So we put that here. Minus 9d times minus d. (9d squared) subtracted. Minus 9d times 2. Yeah, minus 18d subtracted, plus 18d. Okay, we're in the home stretch. Minus 4 times d squared. Negative 4d squared subtracted. Makes it a plus 4d squared. Let's see. There we go, 4d squared. Minus 4 times minus d. 4d subtract. And minus 4 times 2. Minus 8 subtract plus 8. Okay, now in case you're wondering why am I writing in this weird way, I want to line up all the powers so that we can add this all together. Okay, so we add this all together. How many d to the fourths do we have? 1. Oh, that's nice of them. How many d cubes do we have? 0, because we have minus 2, there's a plus 2, minus 9 and plus 9. It's like they planned it to happen that way. And it wasn't me. Somebody else planned it. So, wow, cool. Okay, this one looks like it's going to take a while. Lots of d squareds. You have 6, 6, minus 6. So if we think of those two canceling, we're still at 6. There's a plus 4 and minus 4. Those cancel. So it's like 6 minus 9, which makes minus 3. Okay, the d's. Minus 18d. Oh, there's a plus 18d. That's nice. There's a plus 4d. Oh, there's a minus 4d. So what do we have? None of them. They all cancel. And then, of course, minus 12 plus 8, minus 4. So all of that is multiplied by x. Which means, and recall this equals 0, which means that we really get to the differential equation for x. D to the fourth times x, it means 4/3 of x, minus 3x double prime, minus 4x equals 0. So we've made wonderful progress. We were able to go from 2 equations with 2 unknowns, which was hopeless to do substitution. Now we get down to 1 equation, 1 unknown. Perfect. Perfect. So what's the next thing for us to do? Sorry, what? Well, we're not done with x. We haven't solved for x. But we will go back and do y. And I know you're like nervous, like, we got to do the same thing with y. It's not going to be as bad as you think. Well, it's not going to be as bad as you think in the way that you think. It's going to have its own flavor. Okay. So, but what do we do next? Characteristic polynomial. We've got to go to our R's. So, what's the polynomial here? R to the fourth minus 3r squared minus 4 equals 0. Okay, so we're going to put this to the side. We'll come back to it. All right, so we need to solve the roots. Well, does this factor? Yeah, whoa, that's bold. Now, you might think, I'm not very good with fourth power, Steve, but really, if you think about it, because of what we don't have any cubics, we don't have any just r's, you can really think of it as r squared and r squared squared. So it's really like a quadratic we're trying to factor. And someone says we could factor. How does it factor? R squared minus 4, r squared plus 1? Well, we can check. R squared times r squared, yep, that's good. R squared times 1 is r squared. Then we have minus 4 times r squared, that's minus 4r squared. That's minus 3. And minus 4 times 1 is minus 4. Can we go further with this? Yeah. R squared minus 4, that actually factors pretty easy. R minus 2, r plus 2. R squared plus 1? No, doesn't really factor. So what are the roots? 2, negative 2, I, negative I. Ah, this is good. So, we are halfway, because now we know what x looks like. Remember, this is for x. So, the solution for x of t looks like what? A e to the 2t, b e to the negative 2t, c cosine t, d sine t. All right, good. Are we done? No, but we're like halfway, right? We have half the box filled. Now, why? We come back to the previous page. When I solve for y, what changes here? This x will do what? This will become y. Now, here, it will be a different determinant, but what will ultimately happen to the determinant? It'll become 0 again. So you have this same left-hand side, except instead of x, you have y, which means you also know that y to the fourth minus 3y double prime minus 4y equals 0. Because we're just going to repeat. Everything's the same. We just switched the symbols, x and y. And we're like, wow, that's great. We've already solved that differential equation. And so we're like, perfect, we can write down the answer. That says y is something e to the 2t plus something e to the minus 2t plus something cosine t plus something sine t. And I just have E, F, G, H. Now you might notice two things. That's not in the box. Why did you leave it out of the box? Someone is saying, please put it in the box. No, we can't put it in the box. Not yet. The other thing is, notice, I kept moving up my alphabet. Now, why does it not go in the box? Not yet. It seems too easy, right? To just put it in the box. Let's go back to the original problem. How many derivatives are involved? Now, at the end of the day, what does that mean? I just say, what's the highest derivative of x? What's the highest derivative of y? Yeah, 2 derivatives for x, 2 derivatives for y. So in terms of like the highest derivatives, 2 and 2. Now here's how you should think of it. every time you take a derivative, you essentially lose a piece of information. So every time I'm undoing, I gain something. And when we think of gaining, it's like you have a constant to fiddle with, a knob to adjust, a lever to pull. So since we have two derivatives for x and two derivatives for y, how many constants should we be ending up with at the end? 4. Total of 4. 2 from x, 2 from y. How many constants do we have now? 8. And 8 is too many. So somehow, we've got to figure out how these constants relate. So the moral of the story is this is the right form, but we shouldn't have new constants. In other words, E, F, G, H somehow can be written in terms of A, B, C, and D. Now the question is, how? So that's the second part. So how do we figure out how do the E, F, G, H relate to A, B, C, D? So that's our new question. So I'm going to write it down just so we know where we're going. And can you give me an answer? How do we get the answer to this question? How do E, F, G, H relate to A, B, C, D? Without, keep in mind we only have about half a page left of space available. Yes, I see a hand up.
I'm going to throw a guess that E is just negative A and F is just negative B and so on.
Ooh, that's an interesting guess. One of those is correct, but not both of those. Wah, wah, wah. Yes. So, what do we have that can help us figure out a relationship? What can we do? Oh, yeah, we've got this differential equation here. In fact, we have two to choose from. We're going to go back to this differential equation. And that's going to help us figure out how all those constants relate to each other. It doesn't matter which one you pick, but you have to pick. Given that I said it doesn't matter which one you pick, which one should we pick? Yeah, the top one. Good. You have good taste. That's an important thing. You should develop a good mathematical taste. Now, in case you're wondering, how did we know the top one was the one that we would want? Nicer numbers. You want simple things. Okay, so I'm going to copy that top equation. You can just trust me. I won't lie to you. Well, not right now. So x double prime plus y double prime minus 3x prime minus y prime minus 2x plus 2y. And if you don't trust me, I'll just put it side by side. You can do that little sort of cross your eye things, and the formula will become 3D. All right. So here we go. We're going to put in, because we know what x looks like and we know what y looks like. What is x double prime? Can you do that in your head? Second derivative of this? 4a e to the 2t. Good. Next term? Plus 4b e to the minus 2t. Good. Minus c cosine t. Good. Minus d sine t. Okay, that's x double prime plus y double prime. Oh, someone is really quick. Now, here's the secret. It's the same as this, you just change the letters. Because it's the same form, so it's the same second derivative, other than the letters changed. So, now it doesn't seem so magical. All right. So there's x double prime plus y double prime. Minus 3x prime. Which x prime? 2a e to the 2t. 2b e to the negative 2t. Minus 2b e to the minus 2t.
Minus c sine t.
Minus c sine t.
Plus d cosine t.
Plus d cosine t. Okay. Minus y prime. But again, it's just this. We just change the symbols. So that would be 2e e to the 2t minus 2 capital F e to the minus 2t minus g sine of t, and plus h cosine t. And then the x and y's, well, there's not much thought process. It's just copying. Okay. And at this point, you might be thinking, I don't know if this is going to work. Or you might be thinking, this should be worth a lot of partial credit, right? I think so. I think so. But you know, in for a penny, in for a pound. We've gone this far. We're getting our answer. Darn it. Excuse my language. Okay. Now, what happens next? We plugged it in. We know there are solutions, so it has to be true.
Sorry, I got nervous. Do we want to gather our like terms?
Yeah, we gather. And when we say gather like terms, we gather based off of the functions. Okay, so e to the 2t. So we'll do some math before we gather, right? So let's see how many e to the 2t's do we have? We have 4a minus 6a minus 2a. If we put all those together, 4a minus 6a minus 2a, what do we have? Negative 4a. Okay, but that's not the only place e to 2t shows up. It also shows up over here. 4e, subtract 2e, add 2e gives us plus 4e. Okay, now we'll go to the next term, e to the minus 2t. 4b. Minus 3 times minus 2b makes 6b. Minus 2 times b is minus 2b. 4b, add 6b, subtract 2b, 8b. Come to f. For f, add 2f. Add 2f again. What do you have? And we have 8f. Okay. Go to cosine. Okay, what do we have? Minus c. And then? So we're doing the cosine. So this is where we have to pay attention. We're not gathering c's, we're gathering cosines. So there's minus c. Next line is minus 3d. And the next line is minus 2c. So it's minus 3c, because you have minus c and minus 2c, and minus 3d. Where are the cosines over here? You have a minus g. And here you have a plus 2g. Well, that just makes g. That's not so bad. And then here, minus h. Okay. Sine. Last function. Let's see. We got minus d plus 3c minus 2d. So we could write that as, now I lost track, plus 3c and minus 3d. That's sine. On that part, over here, what do we have? Minus h plus 2h is h, and plus g. All right, so we've grouped. What has to be true about all of these pieces attached to the function? They're all 0. Now, can we use that to help us figure stuff out?
Yes.
What does this first one tell us? A and E have to be the same. So this E was actually an A. Who knew? And now you're like, oh, that was my first guess too, Steve. Why did you make us do it? Well, hold on. What's the next one? Negative b. Oh, yeah, I didn't guess that, Steve. Good. I'm glad you made us do it. All right. So those are the two easier ones. Now for the other two, let's rewrite that. Let's see, what's the color I can use that I haven't used yet? Well, that's a bad choice, but okay. We have two equations, two unknowns. So I'm really trying to solve for g and h. So the first equation, I'll start with this one here. G plus h is equal to, if I move this to the other side, minus 3c plus 3d. So I'm this equation, g plus h, move that to the other side, minus 3c plus 3d. Here, g minus h is equal to, move the terms to the other side, 3c plus 3d. All right, two equations, two unknowns. I'm looking for g and h. How can I solve for either g or for h? Add the two equations, what do we get? 2g equals 6d. So what is g? Yeah, g is 3d. Coming to us in exciting 3d. Now, once you know that, well, you can do something like substitute, right? G is 3d, so 3d plus h is equal to minus 3c plus 3d. So what does that tell us about h? Negative 3c. So minus 3c. So now we have everything in terms of those four a, b, c, d. So we're ready to fill the box. Y of t is a e to the 2t minus b e to the minus 2t plus 3 times d cosine t and minus 3 times c sine t. Done. And in the last 5 minutes of class, no. There's more than 5 minutes of class left. But yeah, it's possible, right? It's possible. Now you're probably looking at this and saying, so do we see these kinds of differential equations often? No, not really. Mostly this is just an illustration of it can be done. Help us flex our mathematical muscles and say, look at us. Look what we can do. We're amazing. Yes, there's a question. Could we have done elimination at the beginning?
Yeah.
I don't think so. Well, I mean, I'll tell you, we don't call it elimination, but secretly what this is telling us to do is, this is saying how elimination would go. So Cramer's rule is sort of elimination in disguise. And so the way you would go through about doing elimination is you'd actually multiply, you take derivatives and second derivatives of these equations, and then you combine everything in just the right way to make it all work out. But finding just the right way is a little bit hard. This says, I'll do it for you automatically. You just have to do a little bit of elbow grease in the meantime. So. All right. Well, that was last time's topic. On to today's topic. Woohoo! Which is we're talking about matrices. So if you've had some experience with matrices before, a lot of what we talk about today, next time, the time after that time, will seem really familiar. And if you haven't talked about matrices before, it's going to be interesting. And there's a lot to say. So this gets into an area of mathematics known as linear algebra. And there are multiple classes taught here that talk about this subject. I think there's at least 3 or 4. And it's a very, very important part of mathematics. So what are matrices? Well, the first way we'll start to think about them is like, well, maybe I'll think about it as a big array of something. And so here we'll have our matrix, we'll call it A. And I have this big array, or if you like, a table. And each entry in that table corresponds to something. And I'm being very vague. That something might be a number, could be a function, could be an operator. If you think back to the previous problem, this is a matrix where we have 2 rows and 2 columns. And what we have is that the entries are operators. And so that's what we mean when we say, yeah, you can do more exotic things. It doesn't just have to be numbers. As we start, we'll focus on numbers. And now what we have is we have this matrix, and we want to just talk about the entries. And so what we'll talk about are things about where are you at in the matrix. So we label things by rows and columns. So if you're in the ith row and jth column, we say this is the entry aij. So these subscripts are just recording where you're at. Now, matrices come in many sizes and many varieties. So you could have a matrix with a very small number of rows, but lots of columns. You could have a matrix with just one column, but many rows. In fact, this matrix here is so nice, we call it a vector. And for the most part, we'll deal with two things. We'll deal with vectors, or we'll deal with things which are called square matrices. And the square matrices comes from the idea is that you have the same number of columns as you have rows. So it would look like a square. It's a very descriptive thing. Okay, good. So matrices, we have this collection of numbers in some array, and we have various sizes. So we want to start doing things with matrices. And where do we begin? Well, we'll start with arithmetic. So that means adding and scaling. So the way we do that says if we have matrices, and we're going to start with adding, and they're the same size, so they have to be the same number of rows, same number of columns, then the way that we will add is entry-wise, which says, okay, I'm running out of space here, but if I have two things of the same size, and I want to produce my third entry, so the way I get this entry here is I come to these two entries, and I say, add these two that are in the exact same spot to produce that new number. So this is how we add. We add the locations up. So that's how we add matrices. In other words, it's what you think we should do. We can also scale, which means multiply by a number. So if I scale a matrix, the way I do it is I scale every single entry by that value. By the way, this formula is just what we talked about just in notational form. It says if I want to know the entry, the ijth entry in the matrix A plus B, I grab the ijth entry in A, add to that the ijth entry in B. Okay. And the other thing is, there's a few important matrices. The zero matrix, well, even if you didn't see what was written up there, if you heard the phrase zero matrix, what would you think? Yeah, all zeros. Zero matrix should have zeros. Very descriptive. You might say, well, why do we care about the zero matrix? Well, why do we care about zero? Think about arithmetic. What's special about zero when it comes to adding? It doesn't change, right? If I have 5 and I add 0, what do I now have? I still have 5. And so 0 is this nice matrix with the property that if I add it to another matrix, I get the matrix I start with. And so arithmetic, because it works just so cleanly and how you expect, everything that you think should be true when it comes to arithmetic is true. So, in other words, if I add the 0 matrix, I get back what I started with. If I take something and I subtract itself, so I take a matrix, subtract itself, I get 0. Well, that sounds right. It doesn't matter what order I add. A plus B, that's the same as B plus A. I can scale two matrices being added, or I can just scale each individual matrix and then add. So in other words, things that we think should be true are true. So that's like, oh, matrices are so cool. That's awesome. We love matrices. All right, so let's practice. How about this example? We have 3 matrices, A, B, and C. We're going to find some things. So here we're scaling, we're adding, maybe we're doing both. 3 times A. What would that look like? Yes, you just multiply every entry by 3. 9, negative 3, 6, 12. Great. Easy. All right, the next one on our list. A plus 3. What's that?
A 6.
Nonsense. It's nothing. It's nothing. They might say, what? Shouldn't you just add 3 to every entry? No, because what am I trying to do here? I have a matrix, a number. I can add a number plus a number. I can add a matrix plus a matrix, assuming they're the same size. But I can't add number plus matrix. There's no rule. We haven't made a rule, and no rule exists. And so since there's no rule, it says, look, this is a silly thing. I can't do it. So it's not allowed. Now, yeah, okay, yeah. 2a minus 3b. Somebody's a lot faster than me. I have to slow it down. So what's happening here is we could do it in many steps, but we'll just do it in one, because I don't have a lot of space. We're going to take the first matrix times 2, take the next matrix times negative 3, and it's okay to scale by a negative number. It's like subtracting. And then we combine together. And so what we'll do is we'll just do it entry by entry, because that's what the rule says. Work entry by entry. So for the top left entry, 2 times 3 minus 3 times 7. 6. Subtract 21. Negative 15. Top right corner. 2 times minus 1 minus 3 times 3. So it's minus 2 minus 9. Negative 11. Bottom left corner. Or if you like, row 2, column 1. 2 times 2, that's 4. Minus 3 times minus 5. It's 15. Put them together. 19. Last corner. 2 times 4, 8. Negative 3 times 0, 0. So we're left with 8. All right. How about negative c? Well, come to c, and what do we do to it? We change the signs. So negating a matrix just says go in, and everything that was positive becomes negative, everything that was negative becomes positive. So it's very simple to just say, flip it around, flip all the signs. And the last one, c plus a. What is this? Nonsense. What's wrong with it? Different sizes. You can only add matrices of the same size. It's like comparing apples with other types of apples. They don't mix. And so that's why we can't make any conclusion. All right, so that says, hey, addition makes total sense. So after you add, what's the next thing you want to do? Multiply. And we're like, oh, okay, we've mastered the art of adding. We add entries together. Life makes sense. And so the natural thing to say is if we multiply, it would seem like, well, we take this entry, multiply by that entry, and we get that entry, right? That seems pretty natural. Well, is it what happens? So we say, hey, here's our guess. Now, there's some pros to that. I want to emphasize. There's some nice things going on here. It's easy to remember. It's intuitive. We like this stuff. It's easy to carry out the computation. Now, those are some really good pros. There's some negative sides to it. It's useless. That's a pretty big negative side. And so we're not going to multiply matrices in the way that's logical. Well, actually, we will, but it's not logical in the way we're thinking. And here's the way we're going to get there. And so we haven't really thought about matrices the way matrices should be thought about. And so right now, when we first see matrices, we think, oh, matrices are these arrays of numbers. But actually, matrices are more. what happens is that matrices are telling us how to move between different types of spaces. So what do we mean by that? Well, our setting is we start in a place where our coordinates are x1 and x2. And now we have this rule that says if I have x1, x2, I can produce a new y1, y2. So that there's this way to go from one space to another space. And so the way it works is we have the coefficients here, right? So to get the new y1, y2, so let me be more precise. If I have a point here, it maps to a point there. And the rule says if I know where I am here, I know x1, x2, then I produce y1, y2 by the following two equations. And these are nice equations. These are linear combinations. And we represent this by grouping these coefficients into a matrix and say, okay, the matrix where we have A11, A12, A21, A22, we'll call that A. Apply that to this point, we get a new point. And we can do that for every single point. So in other words, we have this nice thing where A is a rule about how to go from here to there. That's how we should think about A. Now, if this is making you uncomfortable, then you can stop thinking for a few minutes. We're just trying to motivate the idea. If you're just willing to accept a black box for why things work, then that's okay. But I want to know why things work. Now we're like, okay, well, what's the next thing? Well, if I can go from x to y, why not go another round and go from y to z? So in other words, I have this point, and that sends me to a new point. And that, again, is some map, and we'll call that map B. So A tells me how to go from x1, x2 to y1, y2, B from y1, y2 to z1, z2. And that's what's happening here. So you give me a point, I can move, and once I have that new point, I can move again. Well, what's the thing that you look at this picture and you want to do?
Show it all.
Yeah, you want to cut out the middleman. Say, look, that cuts into my profits. I want to go straight. And so what we're going to do is instead of doing it in two steps, our goal is to do it in one step. We're going to call this BA. Now you might say, why in that order? Well, just because of the way that we're multiplying starting on this side here. See how we multiply starting on the right? Okay, so here's our idea. We know how to go from x to y. We know how to go from y to z. Our goal is to go x to z directly. So that's what we're doing here. See, we start with x, apply the first rule, that gets us to a y. Apply the second rule, that gets us to a z. Now, what we should do is we should think of this as we have multiplied these together. So in other words, we put one right after the other. So the question is, how do I find this magical new matrix? That magical new matrix is B times A. And the answer is it's really not magical at all. We know what y1 is. So what we do is we come and we substitute what y1 is into our expressions for z. We also know what y2 is. And so we substitute for y2. And that's what's happened here. So we substitute y1, we substitute for y2. Here we regroup everything in front of x1, everything in front of x2. Do the same thing again for z2. Now, I will say this is a computation you should only ever do once in your life. So this is your once. And what's the punchline? Well, now we read off the coefficients. So we have b11, a11 plus b12, a21. That's the first entry. And at this point, you're like, that looks more complicated. But what did we do? What did we do? Let's look at this and say, hey, hold on, I recognize things. Where am I showing up in the B matrix? So B11, B12, what does that correspond with? First row. A11, A21, where is that? First column. So what happens is when I want to enter in the first row and first column, I take the first row in the first matrix, the first column in the second matrix, and I combine them together. And that's why matrix multiplication is defined the way it is. So here's the rule. And so what is going on here is if I have two matrices, B and A, and I want to get my matrix out here, C, and here's the ij entry. You go to the first matrix and you grab the ith row. So you want the ith row of the first matrix. You go to the second matrix and you grab the jth column. And then you do what's called a dot product, which means you just multiply as you go along. Dot, 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 dot. And the result is that one entry. So that's how matrix multiplication is carried out. Now, give me one more minute. There's a nice matrix we should talk about, which is called the identity matrix. It's a very important matrix. It's really easy to describe. It's all ones down the diagonal and zeros off the diagonal. So this is what the identity matrix looks like. Now we call it the identity matrix because it acts like 1. What's special about the number 1? Yeah, you multiply something by 1, it stays the same. And so if I take a matrix times I, or I times a matrix, you get back to the matrix. One last comment. Why do we call it the identity matrix? Well, what's happening is it says, suppose I'm going to go from a space back to itself, and it says, here's a point, x1, x2. You gave me the point x1, x2. Great. I'm the identity matrix. What point do I hand back? x1, x2. So the identity matrix says, I don't change. I like things the way they are. I'm going to stay put. All right, that's it for today. We'll start again next time.